I wanted to do something bigger for my third year Internet of Things assignment, so I decided to try and implement a rendering and audio pipeline. For the project, I needed an ESP32 which would load my custom file formats and convert them into buffers and metadata which can be used on the front end to perform the draw call. The formats are loosely based on those seen in games on the original PlayStation, employing many features that those formats had which allowed them to be used on the hardware, and while they are currently not even close to their final iteration, which should be able to be used on the actual PlayStation, progress is being slowly made, and I hope that eventually I get to develop my own game using my own formats for it. I chose, for the purpose of demonstration, to convert the data into a human-readable JSON format, which took up a lot of memory, so in order to allow for networking, I had to create an ASP.NET backend which would read from the serial and allow for GET requests. This way, I can serve multiple devices with the buffer data while still allowing the ESP to perform its own work, such as switching the asset, or allowing it to do nothing until a button is pressed to switch the animation. Converting the vertex and UV position buffers, among others, into a readable array of values instead of passing them as a base 64 string did cause a rather large precision loss, so in a finalist version I will likely switch to doing that among several other tweaks. For now I am presenting roughly the same version I presented back then. Starting off with the ESP, the first thing that we'll notice is that we have an established protocol and are checking for the reset command in multiple places. We do that so that the ESP can be reset whenever we need it to do so. The assets are split into multiple files for the purpose of allowing the end user to choose which parts of the asset they wish to use. For example, this example does not use normals, but they are still included. In a full implementation, we could possibly establish a way to pick and choose the individual asset components. The main thing to notice is that we have a file which contains the names of all assets. Upon request, the ESP will send the contents of this file and wait for the user to select an asset. Once we have selected an asset, all files for that asset are read. They'll then be sent in pieces, every time the request command is sent. Successful uploads will also be indicated by the red LED blinking. The device will also notify the backend when it has sent all of the buffers. It then loops until the button is pressed, triggering the animation change using an interrupt. As for the formats themselves, here is a quick overview. RPF. This particular format represents an index texture with a 16-bit BG array, sometimes referred to as 15-bit, color lookup table, and anywhere from a 1 to an 8-bit per index buffer, which points to a color in the color lookup table, though I implemented only the 4-bit per index one due to resource constraints. For a complete implementation of this and the other formats, as well as an OpenGL project capable of reading them, you can visit my GitHub profile. The device will read the file and construct the actual 16-bit texture. On to the sound. The sound is an ADPCM compressed audio, stored in 16-byte blocks which contain some metadata and 28 samples. The samples are stored in 4-bit nibbles, and in order to be used by a modern system need to be converted to PCM. We interpolate the samples and send the data. Our device assumes it will be a mono audio, though the format can hold stereo sound. Finally, the 3D model. The vertex and normal buffers, as well as any transformations, are stored as fixed point values. Animation timestamps as well as texture coordinates are, however, stored as unnormalized values. In this case, bytes correspond to, in the case of animation tracks, the frame numbers, or, in the case of texture coordinates, values ranging from 0 to 255 in both the x and y axis. The ESP needs to figure out which bone is the root of the armature. It does so by checking if the index of the bone appears in the list of children of another bone. The root should be the only bone without a parent. On to the ASP.NET backend. It is a simple backend made in a couple of hours which has two threads, one of which does the majority of the communication and the other which takes advantage of the read line function and handles the button press commands once the device is in input mode. All in all, it is a primitive implementation which would need more development to handle edge cases such as physically disconnecting the device. Last but not least, the front end. While it would have been better for me to implement everything using WebGL, I was under a time constraint and went with Tree.js. The frontend would periodically check to see if an asset was loaded, and if so, will get it and begin rendering. Even if the asset changes on the backend, it can handle animation switching. The animation data was previously converted by the ESP to handle floating point time values, and as such the frontend can perform the pose calculation and issue the final draw call. I had to place the animation logic on the side of the frontend, as issuing requests to get the current pose many times a second was a bit much. That will be everything regarding my project. This project is just one of the many done on the grounds of the Faculty of Information Technologies in Mostar. Now I will run you through the basic operations.